Hi everybody, it's Professor Mitchell. We're continuing chapter 4 on number theory. And today we're going to be talking about prime and composite numbers. We'll talk about prime and composite numbers, the number of divisors of any whole number, and the fundamental theorem of arithmetic. So as an illustration of the concept of prime and composite numbers, notice that if you wanted to make a rectangle with an area of 18, there are at least 3 different ways to do it. You can make the rectangle 1 by 18, you can make it 2 by 9, or you can make it 3 by 6. And that's because the number 18 has 6 positive divisors, which are 1, 2, 3, 6, 9, and 18. This is kind of interesting. I've never seen anything like this before. What you're looking at is below each number listed across the top, we identify numbers less than or equal to 37, and I think that's just because that's all they could fit, that have that number of positive divisors, okay? So what they mean by that is the numbers 2, 3, 5, 7, etc. have 2 positive divisors. The numbers 4, 9, and 25 have 3. And the numbers 6, 8, 10, 14, 15, etc. have 4. Notice the list of numbers that has exactly 2 positive divisors, which would have to be the number 1 and the number itself, 2, 3, 5, 7, 11, 13, 17, 19, etc. Those are called prime numbers. Numbers that have more than 2 positive divisors, in other words, they have at least one factor other than 1 and the number itself, are called composite. So that takes care of every number in this table except for the number 1. The number 1 is not considered prime or composite. It has only one positive factor. So a prime number is any positive integer with exactly 2 distinct positive divisors. There's a lot of controversy over whether the number 1 is prime. By this definition, it is not, all right? And there are all sorts of good reasons for not considering 1 to be a prime number. We don't have to get into those right now. Any integer greater than 1 that has a positive factor other than 1 and itself, in other words, it has at least 3 distinct positive divisors, is called composite. All right, so to show that a number is composite, you just have to show that it has at least one factor other than the number 1 and the number itself. So the number 1,564, that's pretty easy. You should be able to tell just by looking at that that is an even number because it ends in a 4. Okay, so automatically it's composite, that's all it takes. Now 2,781, we'll have to think about that for a few extra seconds. That is not an even number. So that is not going to have a divisor 2. However, since 2 plus 7 plus 8 plus 1 is 18, remember in the last section we talked about divisibility tests. That means since 18 is divisible by 3, that means the number 2,781 is divisible by 3. So both of those numbers are composite. All right, continuing with this example, 1001, you really do have to think for maybe a couple minutes about a number that divides 1001. Eventually, you find, now I explained this a little differently in the last section. The way I would explain it is to say 1 minus 0 plus 0 minus 1. That comes out to 0. And 11 does divide 0. Therefore, 1001 is divisible by 11. That makes a composite. Now, this last one is a little tricky. I would not recommend multiplying out all those numbers and then adding 1. Although if you did that, you'd probably see pretty quickly what to do next, all right? But what we can say instead is look at 3 times 5 times 7 times 11 times 13. Those are all odd numbers. And when you multiply a bunch of odd numbers together, you get another odd number, okay? And then when you take an odd number and add 1, you get an even number. So this number is even. It's divisible by 2. That makes it composite. Composite numbers can be expressed as products of 2 or more whole numbers greater than 1. Each expression of a number as a product of factors is called a factorization. A factorization containing only prime numbers is called a prime factorization. All right, so here's where we come to the fundamental theorem of arithmetic. Sounds very important, and it is. Each composite number can be written as a product of primes in one and only one way, except for the order of the prime factors in the product. And I tend to be a little obsessive about this. I usually like to write my prime factorizations with the smallest prime number written first and then working my way up. If we always agreed to write them that way, then we wouldn't even have to say this last part. We would just say there's one and only one way to prime factor a number. To find the prime factorization of a composite number, rewrite the number as a product of 2 smaller natural numbers. If these smaller numbers are both prime, then you're finished. If either one of them is not prime, then rewrite it as the product of smaller natural numbers. Continue until all the factors are prime. So for example, if we wanted to find the prime factorization of 84, just think of 2 numbers other than 1 and 84 that multiply together to 84. So I went with 4 and 21. Neither 4 nor 21 is a prime number, so I'm going to continue with both of those. 4 is 2 times 2, which are both prime. 21 is 3 times 7, which are both prime. That means the prime factorization of 84 is 2 squared times 3 times 7. So if you're looking to practice one of these, pause the video and see if you can find the prime factorization for 495. All right, so for 495, I went with 5 times 99. It's very easy to see that this number is divisible by 5. 99 can be written as 11 times 9. Notice that 5 and 11 are both prime, so we stop there with those two. And then 9 is 3 times 3. So the prime factorization of 495 is 3 squared times 5 times 11. Now, this is just showing that it doesn't matter what 2 numbers you start with at the beginning. If I was trying to find the prime factorization of 260, I could start with 26 times 10, or I could start with 5 times 52. In either case, you will eventually end up with 2 squared times 5 times 13, right? So there's 2 times 2 times 5 times 13, and here's 2 times 2 times 5 times 13. So there's where that unique prime factorization comes in that you heard about in the theorem. We can also determine the prime factorization by dividing with the least prime 2, if possible. If not, we try the next larger prime as a divisor. Once we find a prime that divides the number, we continue by finding the smallest prime that divides that quotient, and we continue until we're all done. I usually do it the way that you just saw, but this is another good way to do it. So here's 260 again. Start with the number 2. 260 divided by 2 is 130. 130 divided by 2 is 65. Now I'm done with 2, and 3 doesn't work. 6 plus 5 is 11, which is not divisible by 3. However, 5 works. 65 divided by 5 is 13. And then really at that point we're done, right? Because 13 is a prime number, okay? And then this is just another way to show that work. All right, number of divisors. I really enjoy this topic, right? It's a really clever use of the fundamental counting rule that we talked about. Gosh, I think that was in the last chapter. How many positive divisors does 24 have? We're not asking how many prime divisors, just the number of divisors, any divisors. Well, here are all the divisors. Since 1 is a divisor of 24, then so is 24. Since 2 is a divisor of 24, so is 12. So notice they're just pairing numbers together that multiply to 24. Same thing with 3 and 8, same thing with 4 and 6. Another way to think of the number of positive divisors of 24 is to consider the prime factorization, which is 2 to the third times 3. 2 to the third, which is 8, has 4 divisors, 1, 2, 4, and 8. 3 is a prime number, so it has 2 divisors. Using the fundamental counting principle, that means there are 4 times 2 equals 8 divisors of 24. So let me explain why the fundamental counting principle works here. What it's saying is that you can choose any one of these 4 divisors, 1, 2, 4, or 8, and then multiply it by either of the divisors of 3, 1, and 3, to get a divisor of 24. All right, so since you have 4 choices over here and you have 2 choices over here, that means you have a total of 8 divisors of 24. And by the way, there is a formula for this coming up. Okay, so here are all the divisors of 2 to the third, 1, 2, 4, and 8. Here are the divisors of 3, 1, and 3. So what they're doing down here is they're pairing each one of these with each of these. Okay, 2 to the 0 times 3 to the 0, 3 to the 0 times 2 to the 1, 3 to the 0 times 2 to the second, 3 to the 0 times 2 to the third, and then do the same thing with 3 to the first, 3 to the first times this, 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 and this. Okay, so here's the formula, and I'll try to say this in English. I think I have a good way to say this in English. If P and Q are different primes and M and N are whole numbers, then the number P to the N times Q to the M has this number, N plus 1 times M plus 1, whole number divisors. So in the previous example, we were looking at the number 2 to the third times 3 to the first. And what we found was that the number of divisors was 3 plus 1 times 1 plus 1, 4 times 2. All right, now is where it starts sounding complicated, but it really isn't. In general, if P1, P2, up to P sub K are different primes, and N sub 1, N sub 2, blah, 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 up to N sub K are whole numbers, then the number P to P1 to the N1 times P2 to the N2, up to P sub K to the power N sub K has this number of whole number divisors. Okay, so here it is in English. You find the prime factorization of the number, add 1 to all the exponents, and then multiply all those numbers together. After you've added 1 to each exponent, multiply them all together. And that'll give you the number of divisors. Here are some examples. To find the number of positive divisors of 1 million, we need to first find the prime factorization of 1 million. And so they did that in kind of a clever way. They wrote 1 million as 10 to the 6th. And then they used their exponent rules to say 10 is 2 times 5, and 2 times 5 to the power 6 is 2 to the 6th times 5 to the 6th. All right, so if I add 1 to each of these exponents, I get 6 plus 1 is 7, 6 plus 1 is 7, 7 times 7 is 49. So the number 1 million has 49 divisors. to find the number of positive divisors of 210 to the power 10. That's a huge number. Again, we'll use our exponent rules. So write 210 as 21 times 10. And then write 21 as 3 times 7. Write 10 as 2 times 5. So 2 times 3 times 5 times 7 to the power 10 would be 2 to the 10th times 3 to the 10th times 5 to the 10th times 7 to the 10th. Add 1 to each of those exponents, 11, 11, 11, 11. And when you multiply 11 times 11 times 11 times 11, you get 14,641. This number, 210 to the power 10, has 14,641 divisors. All right, determining if a number is prime. To determine if a number is prime, you must check only divisibility by prime numbers less than the given number. And actually, it's going to turn out it's a lot better than that. When I first read this, I looked at it and I was like, no, you don't have to do all that. But they're getting to it, okay? So for example, to determine if 97 is prime, we must try dividing 97 by the prime numbers 2, 3, 5, etc. And they're saying all the way up to 97. And again, you really don't have to go that high. We'll get to that in a minute. If none of these prime numbers divides 97, then 97 is prime. And it turns out that 97 is prime. Okay, so you can try dividing 97 by all those numbers. And it looks like they're cheating. They only divided it by 2, 3, 5, 7. All right. They just got through saying that we should go all the way up to 97. But again, we don't have to do that. All right, so here's where we're getting to that. Assume that P is a prime. Oh, okay. So they've done 2, 3, 5, 7. And now we're getting ready to talk about what about the other numbers. So now assume that P is a prime greater than 7 and P divides 97. Then 97 divided by P would also have to divide 97. So think back to when we were looking at the number 24. And we said that since 3 divides 24, so does 24 divided by 3, which is 8. Okay, so that's all they're saying here. So if P divides 97, then so does 97 divided by P. And because P is greater than or equal to 11, remember P is a prime greater than 7, so that means it has to be at least 11. Then 97 divided by P must be less than 10. And hence cannot divide 97 because we already checked all the prime numbers less than 10, okay? So the moral of the story is that if n is composite, then n has a prime factor p such that p squared is less than or equal to n, okay? Another way of saying this is when you're trying to determine whether a number is composite, all you have to check is prime numbers up to the square root of n, okay? So for example, 97, I don't know exactly what the square root of 97 is. It's some decimal, it's 9 point something something. So this is telling me that I only have to check prime factors up to 9 point something something, which means I only have to check 2, 3, 5, and 7. Okay, so that's not hard. If n is a whole number greater than 1, and n is not divisible by any prime p up to the square root of n, I'll say it my way, then n has to be prime. All right, so let's look at an example of that. Is 397 composite or prime? So the possible primes p, such that p squared is less than or equal to 397, are 2, 3, 5, 7, 11, 13, 17, and 19. All right, the square root of 397 is 19 point something something, because 19 squared is 361, and 20 squared is 400. So the square root of 397 is somewhere between 19 and 20. So we need to check all primes up to and including 19. And they didn't show all their work here. I think you can tell just by looking that 2, 3, 5, and 11 don't work. Let's talk about 11 again. 3 minus 9 is -6. -6 plus 7 is 1. And 11 does not divide 1. We did not talk about divisibility tests for 7, 13, 17, or 19, so you could check those with a calculator or by long division. None of them work, and that means 397 is prime. What about 91? Is it composite or prime? This would be another good time to pause the video and try this one. First, think about which prime numbers do you need to check. Well, you only need to check 2, 3, 5, and 7. All right, well, clearly 2, 3, and 5 don't work. But 7 works. 91 divided by 7 is 13. So 91 is composite. All right, and we'll end by talking about the sieve of Eratosthenes. One way to find all the primes less than a given number is to use the sieve of Eratosthenes. If all the whole numbers greater than 1 are considered or placed in the sieve, the numbers that are not prime are methodically crossed out, or drop through the holes of the sieve. All right, the remaining numbers are prime. So, you know, when a sieve, you know, imagine a container that has some holes in the bottom and you've got some dirt in it and you shake it and some of the dirt falls out. That's kind of what they're talking about here. All right, so here is a demonstration of the sieve of Eratosthenes. We're going to use it to find all prime numbers up to 100. So the first thing we're going to do is cross out the number 1 because we know it's not prime. Then we're going to circle the number 2 and we're going to cross out all multiples of 2. We know that 2 is prime, but multiples of 2 are not prime because they have a divisor 2, right? Now we'll do the same thing with 3. We will circle the number 3 and we will cross out all multiples of 3 that are not already crossed out. So for example, keep your eye on the numbers 9, 15, 21. Okay, they just got crossed out. All the odd multiples of 3, because the even multiples of 3 were already crossed out. Now we'll do the same thing with 5. We've actually already crossed out most of the multiples of 5. We don't have 10, 15, 20. Oh, 25 is about to drop out. We already lost 30. We're about to lose 35. Okay, so we're just, well, we're going to lose everything in this column, really. Okay, there they go. And now we'll do the same thing with 7. I noticed we just lost 49, for example. And now, if we were considering 100, the prime numbers up to the square root of 100 are just 2, 3, 5, and 7. So that means that everything that hasn't already been crossed out is prime. Right? So when I click, all of those numbers are going to get circled. So there you see all prime numbers up to and including 100. You could easily do the same thing up to 200. Okay. Doesn't take too long. It's just a little tedious. And that's going to do it for section 4.2. We've got only one section left in chapter 4. So we'll see you next time.